My name is John Cody. I'm an engineer from Vancouver, Canada. Today I'll be talking about scattering amplitudes in physics and Platonic mathematical structures. This is based on a talk given by Nima Arkhani-Hamed from the Institute of Advanced Study at the Amplitudes 2022 conference. There's a YouTube video given at this link here. I will provide a link in the description above and at the end of the video to this talk given by Nima. And so what I will do is I will combine the ideas about the geometry of scattering amplitudes presented in the first half of this talk by Nima with the math of universal hyperbolic geometry to see if we get the kind of mathematical structures that he is looking for in this talk that he's given. So first I will recap the ideas from Nima's talk, as well as some of his other talks on YouTube, and then I will explore these ideas from the point of view of universal hyperbolic geometry. So Nima is looking for a certain kind of mathematical structure in the Platonic world of ideas that have certain properties, and we will see that the mathematics of universal hyperbolic geometry, abbreviated UHG, also has these properties that he is looking for. Okay, so we're talking about scattering amplitudes, where you have in particle physics, where you have two particles in and two particles out. And they would scatter off each other. So in this business of scattering amplitudes, they talk about on-shell versus off-shell particles. So the particle is given by this momentum, which consists of its energy and its momentum vector, and it's given by this Einstein relation, p squared is equal to e squared minus p squared, and that's equal to m squared. And that's called on-shell, when p squared is equal to m squared. And when you have this is a Feynman diagram here, so you have two particles in, they scatter, and you have this propagator p here, and that's where the momentum p is p1 minus p2, and when typically this propagator is an off-shell particle, and it's given the denominator is p squared minus m squared, and that's not zero, so it's like p squared minus m squared, and when it's off-shell, then this is not zero. When it's on-shell, it's zero, and you get a pull. So here we have a diagram of the scattering process, indexed by these numbers 1, 2, 3, 4. So this is particle 1, particle 2, particle 3, particle 4 in. You get this Feynman diagram, and there's a virtual particle m that is created, and then they scatter off in 3 and 4 as particle 3 and particle 4, and that's also represented by this polygon shape, where you have particles P1, P2, P3, P4 coming in, forming this shape, and particle M is a point inside the shape. So we have what's called resonance when P1 plus P2 squared, so P1 plus P2 squared goes to M squared. So, and the scattering amplitude is given by this expression 1 over P1 plus P2 squared minus m squared, and we get a pole here when the virtual particle becomes real. So when P1 plus P2 squared is equal to p squared, then this becomes real, and it blows up. So quantum mechanics tells us what happens to the amplitude when you get a pole in the denominator here, and what happens is it factorizes into two pieces. So two amplitudes of lower point amplitudes. So pi is equal to m squared. So particles come in, get this intermediate particle, propagates, and then the intermediate particle decays into particles 3 and 4. So the rules of space-time and quantum mechanics are reflected in this scattering process. Locality tells us that there are only poles when P1 plus P, when all the sum of the momenta squared becomes m squared. So when there's a pole, that only occurs when P1 plus P2 plus up to Pn is equal to m squared. And unitarity tells us what happens on the pole, when the pole happens. The expression, it factorizes it into two pieces. So when a subset of the momenta goes on shell, meaning the particle becomes real, when p squared minus m squared, when there's a pole here, then we get this factorization into two pieces. Okay, so that's the scattering process. So I will summarize what Nima talked about in his talk. The first half of his talk, he says that on-shell momenta is in kinematic space, and the ultimate goal is to find a different question directly in on-shell kinematic space whose answer is the scattering amplitude A. So he's looking for some function A of the momenta of the on-shell momenta, and that's what he's looking for. And is also looking to see simplicity and structure in the answer, and that drives progress in this field. So trying to find better ways of calculating the amplitude and seeing simplicity and structure in the answer. Simpler than summing over all Feynman diagrams to get the answer. So he is searching for a new kind of question that involves new mathematical ideas, and he never wants to talk about virtual particles, which is the propagator here. That's a virtual particle. He only wants to talk about on-shell particles, momenta that are on-shell. So he talks about discovering some shapes that live in kinematic space and figuring out how to get the amplitude from it by connecting a function or a differential form to a shape. So he's talking about shapes and determining a function for this shape or a differential form for this shape. And he says that what is this kinematic space? It gives 4 options. It's the space of n null momenta, where n is the number of particles. He says the kinematic space can be the space of Mandelstam invariants, that is of dot products of pairs of momenta. He says the kinematic space can be the boundary of Minkowski space, where points on the celestial sphere, where the energy of the particles have a direction and they hit on the celestial sphere. And he says that the kinematic space can also be option 4, the labeling by twistor variables. And he says there is no such thing as a local quantum field theory that lives on the space of n null momenta, and that is a problem. Or thinking geometrically in terms of the celestial sphere, he says that there is no notion of locality at all. He says there's no notion of locality or time for the thing that we care about. And that's why he says the things that he will be exploring are going to be adventurous and involve guesswork. He wants to discover what the rules are for this new way of looking at things in this subject. So the most important takeaway is that the poles or singularities of the amplitude function is reflecting the boundary of the shape. So at tree level, for scattering amplitudes, the most important feature of poles and singularities is factorization of the product of 2 lower point amplitudes. So he's saying when this point goes to the boundary of the shape, then there's a singularity, we get a pole, and when we get a pole, then there's factorization into two lower point amplitudes. So he says locality is reflected in the fact that amplitudes have a singularity when some of a subset of the momenta go on shell, that the singularities are poles. And if we are looking for some kind of structure in kinematic space that is going to tell us about amplitudes at tree level, then it should know why the poles look like the sum of momenta and that the object is splitting into the product of two lower objects of the same type. So again, locality tells us where the poles are, what the singularities look like and where they are, and quantum mechanics tells us what happens in the neighborhood of the pole, that it breaks up into two pieces. So when there's a pole here, the amplitude breaks up into these two pieces. So if you have a function that is local and unitary, then that is the answer, he says. So he says his concrete strategy from a different video of his is to find a different question directly in the kinematic space to which A of the momenta, where P1 to Pn are the momenta, is the answer without referring to space-time and quantum mechanics, but which nonetheless gives correct poles and correct factorization. That's what he's looking for, and he goes on to show that the scattering of 4 points here can be reflected in a shape. The scattering of 5 points can be reflected in this shape with this triangulation, but a triangulation where you have crossing chords, that's not allowed, and this triangulation would not be allowed. So a triangulation where the chords for locality is when you go to the boundary, and unitarity is when you factorize on a pole into two lower point amplitudes. Okay, and he said in a specific sense, amplitudes are to be thought of as the volume of some polytope, where he puts the volume in quotes. So that would be, this polytope is this quadrilateral shape here in green. So, and he's saying different triangulations of the shape make different properties manifest, such as locality and unitarity. He says our solution should be thought of as providing one class of triangulations, but we need to more deeply understand the object that's being trained. And he goes on to say that another example of MHV one loop amplitudes is the volume of these two polytope shapes. One is triangulated this way, which would give you a property of locality, and a triangulation like this would give a property of unitarity. Okay, so then he goes on to say, this is Plato's world here, the School of Athens, and he says, we are looking for the kinds of mathematical structures in the Platonic world of ideas that have this property that there are a set of objects that are indexed by n that is going to be the number of particles, and that needs to have the property that when you go to the boundary of this object, the property that has to when you go to the boundary of this object of the other boundary has to factorize into the product seen before of other objects a feature of the same type that you have seen before. And this should be a feature of the before. We have, so that's what I was indicating before. We have a scattering process, It's indicated by this shape here, where m is the internal particle there, and when m goes to the boundary of the shape, then we get this factor. We get a pole. We get this pole, and the virtual particle becomes real, and then we see that there's this factorization into two lower point amplitudes. So again, locality only poles when a subset of the momenta go on shell, and unitarity is this factorization. And that's what he's looking for in the Platonic world of ideas, he says. So, and then he goes on to say, if we find these interesting geometric structures that have this self-factorizing property on their boundaries, then we are close. We have an opportunity to look for some way to ask a question of that structure whose answer we'll interpret as an amplitude that depends on a bunch of momenta. But this basic fundamental fact about the factorization of the structure will turn into factorization of the amplitudes. In that way, locality and unitarity will be outputs out of this object rather than inputs that went into it. And that is roughly the kind of thing that he is after. So what I'll be doing in the next video is we'll look at this from the point of view of the mathematical framework of rational trigonometry and universal hyperbolic geometry, which takes the point of view that geometry is really about formulas. Geometry looked at algebraically with algebraic expressions that capture relationships between geometrical concepts. So in the next video, I'll dig into the math of this universal hyperbolic geometry and then triangulate a shape and see that we get this structure that he's after in an algebraic expression, where we get the poles. When there's a pole, it factorizes into two pieces. Okay, so thanks for listening, and stay tuned for part 2.